to it, and the clients who won't run streaming.
Gotcha.
All right, I'll turn it over to Ryan.
Cool. Well, on to programming. This is directly ripped off of the articles of F# Fun and Profit. So lots of the ideas are, copied from there. I've added a few bits that I think are relevant and things that he possibly doesn't go into that you should do, because he just describes this is a set of things that I have available, and this is what you can do with them, not why it's relevant, what's important about it. So yeah, what problem are we trying to solve? So this is a list of all the different error handling systems that I can think of, exceptions, and sort of the node style where you pass around callbacks that have one value on the left that is an error, one value on the right that is the result. You have to check if null, etc. on the error to check whether the result is the right value. Default values, we're all guilty of just retaining null when we shouldn't, and no exceptions come from that. And result objects. So we have an object that has like a flag saying true, a value, and an error, all on the same object. Doesn't force the consumer to use it in any appropriate way. It just kind of gives you the values, and you have to deal with it however you deal with it. So, I'm basically every section is going to explain why each of these is a problem, and we're going to try and build a set of ideal things that we want from an error handling system, and explaining sort of how that leads into relay-oriented programming. So exceptions are basically fancy go-to statements with sort of special syntax. So, it will eventually at some point unwind the stack, find a catch. If it's the right type of exception, give you a code block to run. One advantage of exceptions that everyone seems to enjoy is that they're deferrable. So I don't have to handle this here, the place where the error has happened. I have to handle it all the way at the top or any intermediate point from top to bottom, which is a good part of exceptions, because if we're still using them, there's got to be some reason why we use them. Obviously, it means that every line of code that you're doing could be doing something completely random. Your APIs don't actually say, unless you look at the documentation online, what exceptions they actually throw. So your code doesn't force you to handle all types of errors. You just assume that it does, and then it breaks, and then you have to go debug it on a remote server that doesn't have any good tracing, and you don't know the stack and the objects available. Whereas it's obviously the most simple implementation. So that's how I think about exceptions. And the main issue is magic code paths. Just complete tangled mess of, I will catch this exception here, I will rethrow it with different methods, and just that kind of undecipherable code is common in so many places. So the pattern that node uses the callback error result. You obviously have to check that the error exists before using the result, but you don't have to. You could just look at the result value, and if it's null, handle if it's null. You don't have to use the error value, it doesn't force you to. So it's non-deferrable, so you have to handle it, you have to pass it round, so it leads to very verbose code and callbacks. So it becomes like that. It just you have to handle it every time, every layer. So it's good in the respect that it has at least made you aware that this thing that you are doing can fail, which is half the battle. Too much work with it. So default values, if you're in doubt, just return default value, or none suffers from the same option. You should not use option for error handling because it's the same as null. It tells you that there is something wrong with this value, but it doesn't tell you what's wrong with that value. You still have to handle it. So this is a very nice gift that I found. Here those. So yeah, so there's no explanation of the error. So if you want to report the error to a user, or even just for yourself, debugging the error, you don't know where did that option actually fail, because I have 1,000 different places where I use option. And my favourite result objects, obviously everyone has got to a point where I need to return something here, and I don't want to do any of the things that happened before. And this is, I've written this code many times, and it has, I've copied the same thing from last time. I'm sure I changed that. So I'll just go over the issues. Obviously, you have to then assume that you don't know what the success value, what the error value is from the type. There's no way of knowing. You have to look using IntelliSense, what is the actual value that I want. I don't have to check has error. I don't have to check this. Like that flag might not be set, and this value could be set. Don't know whether it's an actual value, and all the things that come along. It doesn't force the user to handle it. So obviously, I'm talking about functional programming specifically. There is a pattern quite common in the Haskell community called either. So I have a left value or a right value. So who can guess what the error value is?
Well, I think I know, but yeah, it's not obvious.
It's not obvious.
Like
It's the
left.
yeah. So it's the left value. So as a consumer, as someone who's never programmed in your life, how could you look at that and say, unless this type has the word error in it, from a consumption perspective, and then that just adds a ridiculous amount of boilerplate. You don't want to have to append the word error to every one of your error types. It should just be an error. It's the thing that has happened. And it leads to you pollute your code with the concept of left and right everywhere as well. So if there is the case where I want to declare if it is the right value, I'll do a map right. So I'll say, if I have a right value, I want to map it to a different right value. If I have a left value, I want to map it to a different left value. I don't think your API should be talking in terms of left and right. It should be talking in terms of right and wrong. So this is the list of things. You want something that is quite simple to consume, simple to use, and it's unambiguous. So as a consumer, you are forced, you know exactly what the errors and result types are, so there's no ambiguity as to how we use it. And you can defer errors. I think that's the big thing that exceptions have. You can choose to look at the error later. You don't have to use it. You don't have to care about it. You just care, I'm going to write a pipeline, at the very end I'm going to use the error and unravel it. Or I'm just going to pass that function up a level and I'm just going to keep deferring it all the way to the top. Honest APIs, I obviously don't want to have a look at the documentation to see if there's no reference exception going to be thrown in this. You just know that this is the exact behavior that you expect. Explicit consumption. So, this is the result type. I copied this from F# core because the latest version has this in now. So you can just use this in your F# code and it is available. So it's obviously become enough of a pattern now. Obviously, F# doesn't have it either. So this is what you've got. Either is useful if you have actual choice between two things, but other than that, you might as well just use discriminated unions. Yeah?
What's the difference between either and choice of two? Because that's a thing.
It's essentially the same thing. It's just that
It's like different names or something.
it is a two-case discriminated union that you can infer special things because it is a two-case discriminated union. That's essentially it. Just gives it a little bit extra meaning to the two cases.
Does F# have union types?
Sorry?
Does F# have union types?
Yes, it has specific discriminated unions. So this is an actual union type itself. So that is how, discriminated unions are a fundamental piece of F#. So this is how you define discriminated union. You say type, you say your obviously qualification and your generic arguments, and you define the individual cases, and then you say what each case's type is. That is if that wasn't explicit, good question. So there are three parts to handling errors. There is creating the error, there is deferring the error, and then there is the actual consumption at the end. So how we create it, how we pass it along, and how we, at the very boundaries of our applications, because we can't serialize these because they're not very friendly for the majority of our serialization libraries, don't have the concept of unions. You have to convert it into another result object, pass it outside of your domain, and convert it back, which I think is a fair assumption to make. That's what a lot of functional programming languages do. They take a raw input and they convert it to a domain model that is modeled in sort of unions, etc., and then pass that along pipelining consumption. So this is how you will create a result value. So the type of this will be string in, and it will be result int string out. So as we've seen in F#, we don't have to define our result types, obviously because types are inferred. We don't actually have to define, if we didn't have an error case, it would just infer that I have a result of int and b. It doesn't matter what the error is, because I've not actually told the compiler what error I actually have. So we can wrap existing APIs, and all you have to do is you have to pass your actual value into the error or OK function, and it will infer that that is a type of result from the layer above. So yeah, there's the API. And this is where the railway-oriented programming comes in. So you imagine everything like two sets of tracks. You have an error track and you have a successful track. So obviously green, red, hopefully that's a universal symbol for good and bad. So this function accepts something outside our domain, possibly a deserialized object from our web endpoint, and we're basically going to assert some condition, and we're going to branch out into an error path or a successful path. So once we've actually got a function that can create it, it's super simple in terms of how you actually build it. You have to pass values along the pipeline. So we've taken the value in, that's a string, we've parsed it, so we now have a result of string, and we have a result of int and string. So there are three fundamental operations in the F# core version of result. There's bind, map, and map error. So what we're doing here is we're defining a set of operations, things that happen in a list. If we're going to check some condition, if it fails that condition, it will not move on to the next step because it is in the error track. So we can think of the error track as like a fast path out of our application. The moment you hit the error track, it will sort of, every map and bind function, it will ignore from that point onwards until we hit either explicit consumption or we change the error type itself. So we have bind, which takes the integer value we get, check this greater than or equal to 10, explicitly pass that value on. So a bind is essentially a flat map or a select many. So that's the common terminologies that are used across the sort of the monadic systems. And map would be equivalent to map or select. So if we think of it in terms of IEnumerable of string, we have select. Select takes a type of T and returns a type of U. And that is basically what we're doing here. We're taking that integer x and we're timesing it by 2. We could do a toString on it, and that basically changes our result type from the level below for the next thing handling it. So we can.
So is it? Is it fair to say that the difference between map and bind is a map can return a result of T and E,
Yes.
whereas map bind can return a result of T and E, whilst map has to return a T.
Yes. So map is about if you always write pieces of code that deal with your business logic or your domain, and that will just be straight operations. And think of map as the way of exiting the world of results and allowing you to do whatever you want to do inside of there, and then coming back out so you can sort of continue that pipeline. And as I said, bind is a way of sort of inserting points of failure inside of your application. So it's very explicit. Map is something where nothing can go wrong. Exceptions can still happen in F#, but they should be exceptional. They should be not something that you write into your common application. And bind is something you said, it can fail here, so I have to explicitly create the values. So map function, as you said, it basically takes a successful value, this is your function here, and it basically takes from T to U. So if it is an error, it just skips through. Nothing happens, no code is invoked if it is an error. And we'll see that later. I've got a bit of an example where we can step through and see how it follows through the pipeline, as it were. So yeah, bind is obviously, if it is success, if the value that is passed to you is successful, then you introduce a construction function, a point of failure, and that can branch out to the error path, and then that can fast path all the way to the end. And obviously map error. The inverse of map is you want to change the error type, because I imagine if you want to compose these errors together, so you want to add errors together, you might have a different error type, so you'll want to map the error to be a list of string and then add the list of strings together later. However you define I'm not going to talk in terms of how you define your error objects, just that they exist, and you could use discriminated union, you could use a string or any type of object.
I appreciate you probably just said this, I'm just kind
Yeah,
of
no,
catching
that's
up.
fair enough.
So map effectively filters out errors.
Yes.
So after a bind, you're probably going to expect to see map followed by map error regularly.
Possibly. Depends if you have a ridiculous number of steps that could all exactly fail. You could have a map at the beginning. So you're basically, when you have a map, you're saying, I don't care about the fact that I just want to insert some code that I've written into the pipeline. Doesn't really matter. But yeah, it's like,
Well, I guess it doesn't filter errors because you can still have an error. If you have an error happen before the map, it will still propagate to after the map.
yeah, so it doesn't explicitly get rid of it.
So you still have the whole stream effectively.
Yeah,
It's just you're only operating upon the items which have an
If
error. and those
it's a
items.
successful case, then apply this function to the successful
Oh,
case.
that's cool. Okay. Right.
Yeah.
so that's the deferral nature.
Which
Yeah.
knows nothing about the idea of a result or success or failure. It's just like, this function does not need to know about it, wrap it up.
Yeah.
If it's successful, that function gets called. If it was unsuccessful, the function never sees it, but the function itself remains kind of unsullied by the idea of success or failure.
Yeah, it's just interesting then that the stream defect be maintained behind that, because obviously it's mutable, right? So your maps and spit this stuff out, but it really is operating upon items in it, yet your streams being duplicated in effect, and mutability. There's some quite cool stuff going on behind it.
Definitely. And it's building upon all the great parts of F#, such as type inference and mutability, like you're saying, and the union system. And so it's really leaning heavily on the compiler to do this kind of stuff for you. So we get to the consumption. So we defined a discriminated union very similar to this. We said we have an OK branch and an error branch. So what this is doing is basically, I have fit the boundaries of my application. I either have to choose to create a result object to pass it and serialize it, or I'll actually just throw an exception here. So I'll hit the point where I can go no further, and I can then throw exceptions that could be more meaningful because I've built up a comprehensive object that describes the state of the application more, or build the result object earlier where you have has error, etc., set of states. Or if you could return, for example, if this is okay, we could return a 200 result of a type, or we could return sort of a 400 for the error case, and that's where you can take advantage of discriminated unions to have concrete error and success types. And it fits very well into the sort of stateless web architecture very, very well. So this is as far as I've got. I've got a ton of demos to go through, and this is the section of the slides to talk about. I've obviously only talked about the built-in version of results that comes with F# core. There is a different version which is much more fully fleshed out called Chessie. I'll show that example of that later and how they differ. But there are a number of cool things that you could do with results. So who here has heard of computation expressions? Yeah. I'll show you what they are, but they are a way of abstracting away that there are that you are working in a monadic world. So F# was one of the first languages to introduce async. I don't know.
I don't know.
Don't know. As like a type, async type, like a promise, it was one of the earliest, I think.
Yeah, I think we're working it fed back into the async await
Definitely.
C#.
And it was very heavily influenced by that. So I'll just kind of show you how that ties in to that. Result aggregation, so I have two errors, how do I add them together? That is obviously an important problem. If you're working on a validation pipeline, you don't want to have a set of cases where I have fail, 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 and then a pipeline pass through. Sometimes you want to evaluate a whole object and get all of its errors, bundle them together, and save them back to the client, especially if you're in an environment where retaining all of those errors, like a web form, is very important, because you don't want the user to constantly have to fight against, I fix one error, another error appears. You want to get all the errors that are possibly findable in that sort of space, and then moving along.
Can you do that result aggregation with any of the other sorts that you talked about?
So you
It
can
sounds
use...
quite a good advantage.
Yes, so I'll show you the code that Chessie uses to do aggregation, and I'll show you the code that my library uses to do aggregation, and we'll kind of compare how you would do that. But it is going to be a bit more ad hoc. T, side effects, so if you want to log at a specific point, you can write a T function which basically accepts your result value or error value, and it does nothing. It retains, it's a void or an action in C#. So you can log out, or you can sort of update a transaction in the database somewhere in your pipeline. And I don't even know how you say that. That's the one. No one's ever said it out loud to me before, so there you go. That is just a way of defining your operation so that your code doesn't look like it is working in binds or maps. It just, you define a new type of operator to add together, to build your pipelines. So I'll show you an example of that as well. And we are at the end of that. So just break out of here. So is there any questions before I move on to the next set of things? I know I've gone through that quite quickly, so slow me down
Are there any already existing or well-known constructs in, let's say, C#, which I guess most of the people here are all familiar with,
Yes.
that are as more similar to these ideas than exceptions or whatever? Is there any kind of frame of reference for
I think
C#?
the best frame of reference is always IEnumerable. It is sort of the functional gateway drug for C# developers. If you think of everything in a frame of reference of how you work with IEnumerables and how you pipeline them, I think that builds an understanding of what you can do and the kinds of code that you write. There's obviously operations that aren't available in IEnumerable that are available in Result and inverse. So it's all about thinking about your exact sort of problem sphere, and you can build sort of higher level operations on top of the fact that you know that you have an error and a result. You can build whole frameworks around that have tons of weird esoteric functions for every single person's use case. And it's more about giving you a recipe to doing stuff rather than saying, this is how you do error handling. It's about giving you all the implicits for doing that.
I think it's important to also stress that what you're showing us with results, option, all that, there is no magic. It is all just based on discriminated unions and higher order functions. So there's no magic happening under the hood. And in fact, as you said, results has just been put in the language now.
Yes.
But it's just been put in because everyone was hand rolling their own. And like all these things, like option as well, you can see it written in the language, and it's just a discriminated union. That's all it is. There is no magic happening under the hood again.
I think my history.
Don't mind the police, let me go and see.
I think I saw it then. Primitive types. So yeah, we'll just have a look under the hood and see how we actually define results.
You zoom this a bit bigger.
Yeah, that's a good point. Somewhere in here, I've seen it because I copied it. There we go.
There we go.
So yeah, this is obviously, as I said, it is copied exactly word for word from how has been obviously in that slide. There's obviously a few extra bits. So struct, so there's a value type, so it should be more efficient than using sort of value, sort of object types to allocate on the stack in terms of the immutability. So the compiled name, that is how you will see it from C#. If you try and consume this, you can write consumption layers, but you'll probably have to do that yourself. Just why I wrote my library, because I want to use this pattern in C#, but using F# primitives is just not the greatest thing. And interestingly enough, there are these two extra flags here. So the great thing about this is you can compare two result types to each other. So if you have two results that are both successful values, it will, under the hood, call the equality member of those two t values, so they're directly comparable. So if you want to assert that this pipeline returns a result, that is successful, you can actually construct the result to compare it directly against in your assertion. So it removes that level of boilerplate that you have to do typically when you're deconstructing discriminated unions. I'll see if I can find the operations as well. I saw them. Yes. So the functions that we've talked about, bind, map, and map error, are built from fundamentally consuming discriminated unions. So let's just start from the beginning. Mapping results, so we have a mapping function, we have the actual result itself, we will pattern match on that result. If it is an error type, we just return that error type, like we said. And if it's okay, we will return okay of the mapping function and pass that value in. Very easy to define. Map error is the same, but with the error case, we still have a map, have a result. Very easy. I'll show you how to define operators to build extra things on top. And the bind function is essentially the same as the map function, but we just don't wrap it in an OK. And implicitly learns that because I am returning, I have an error here and I have a binder here, that should be a result, which is one of the great things about F# is it's type inference. You're never, we've not been explicit anywhere here saying this is using or retaining result values. All we're saying is I have an OK value here, I have an error value here. That learns that is how you construct a result. So it's a pretty nice way of defining your utilities. So this is something a sort of a set of examples. So I'm going to show you how this would look in your code and how you would sort of build your pipelines. So we've got the construction function there. We've been over that. This is how you create an error, and you can slot that construction function into a bind function. And this is the composition operator. So basically saying we have a function which returns a result, and we have another function which returns a result. And obviously F# has inferred that the first function will accept A, and then the second function will accept B. The first function retains B, which then feeds into the second function. Then we pass in A at the very beginning, and it retains D. And it's very intelligent in that way. All we're defining is a composition function where we add result.bind on that switch function, and we compose that together, and we've defined a brand new operator. So you could do brand new operators and build up your logic in very short lines, succinct pieces. So I'm using inide here as well, which is a F# extension for VS Code, and it is almost better than Visual Studio. A lot of people do use it in their day-to-day lives, and this is one thing that I've seen in inide that isn't actually present in Visual Studio. The type signatures that are sort of there, you can change them so that it automatically adds comments. with that type signature, and you could possibly commit them into code if you wanted to sort of, because F#, one of the complaints about F# is because the type inference system is so powerful, you have no idea if you look at a code review, what the hell is this thing doing? Because you kind of have to internalize the logic of the entire compiler to know how the inference system would work. Especially when you've got public APIs, I could just change this line here, and everything above that depends upon that is going to change its type in subtle and weird ways. So that's quite useful. So we have another construction function, and I'll show you how two construction functions can be added together. So our pipeline, we're going to add together a bunch of smaller functions to build a validation pipeline. So we're going to bind on that function there, and that gives us the first element in the composition function. We add on the second bind function, and this block here will have the same will have an outward signature of string result in string. So the way that is one of the powerful things about F# is the functional composition. We'll map that value, and then we'll return the map of the error. So if we have a look at the slides from before, the difference is the composition operators. So we've not had to say result.bind and pass in a lambda function. I was passing in these lambda functions earlier. I don't think there's anything really to explain more with this pipeline. I'll show you how it steps through. So we get all the niceties that we do in Visual Studio, and obviously Visual Studio Code, and there's not as great debugging support, but it is obviously getting better and better and better. So the first thing we've done is we passed in value, we're going to pattern match on that. We're going to pass that value into our pipeline directly. That pipeline function will hit and compile this functions list. We're going to pass that value into the construction function, so we're going to pass that, so just hover over here, we've got 11, and that is an int, successfully passed. And I think this one should pass all the way through the pipeline and come out the other end successfully, because it should fit in between greater than 10 and less than 100. So the first thing it's going to hit is result.bind. So we have the result.bind looks at the underlying constructed value and determines that it is okay, so we can invoke greater than 10. So this is the composition function. And the composition function has decided that we can actually go in and hit that first value. I'm going to check x greater than 10. Okay, that's fine. Move on to the next stage here. So compose those functions together and move on to that next stage. Invoke that. It is less than 100. Fine. We're going to map it, so we're going to multiply it by 2. And we're going to skip over the map error because there's no error. So very easy to see. And then we're going to pattern match. That value is okay. And then we're done. So we try 9, and I'll just run it because there's no point stepping through that entire thing again. I'll show you what happens when you hit the error branch. That's probably a better thing to do. So obviously we're evaluating the result of that error. That last line evaluated that we have an error value. We're going to move on. And there we go. We output error value must be greater than 0. And we've not used exceptions or explicitly had to check, have any sort of conditionals in there at all. We've got pattern matching, which forces you to handle each case. So you can't just say, I have a result and I want to just get the value. You can define an operator called return or fail, but it's not advised because you're basically sort of cheating and just throwing exceptions again, which is what we want to avoid with this whole system. So I'd say we have a break here because I've got some other bits. after this, and we'll talk about Chessie and computation expressions and everything else that comes with that. Any questions at this point? So, this is Chessie. It looks very similar to the built-in result type, so it has the exact same method signature. You open a different namespace to get at the value, and result is just available to you.
So I can just stop you before you go on. So, in the first half, I was confused why there were multiple words on the like the definition lines. So line 4 was the validation pipeline and pipeline functions initial value. I don't understand that.
Which bit, sorry?
So it's the line 4.
Line 4, yeah.
What is validation pipeline doing there?
That's function name.
That's the function name, and then all your arguments afterwards. So, no. So do you know the way that F-sharp type signatures work? That's probably a good point. Do you want me to go through that?
I could use further
That's the
explanation.
question, really.
Yeah, fair enough. So in like C#, we're used to the idea of having multiple arguments. You have, you can pass in X number of parameters and return one. It's tuple, you can return many, but in a single value. Whereas F# is slightly different. It only has one input, one output. Interestingly enough. So under the hood, I essentially think that, imagine this is your first input. What it will do is it will create a function that passes that input in, and it will return another function that accepts that input, and then that final function will do that. So that's basically how you query operators. So, for example, if I wanted to get rid of pipeline functions here, we'll just see how it changes the operator significance. So what was it before? Let's just get familiar. It returns A of B. But now it returns a function which accepts a list which returns a result. So pipeline functions was passed in. So what we're basically saying is this part is we're adding the pipeline functions to our thing that iterates over them. And if we get rid of pipeline functions from there, it returns as a function that we can pass our pipeline functions into. So that's how you, in a roundabout way, try to start reasoning about the type system.
I've got one of the previous slides. I'm sorry to start taking.
No, don't worry about it.
But the definitions of the bind map functions or results, I think it was. They had the word mapping.
Yes.
Different method names.
So that was the argument. Mapping was the. I'll go back to it. Do I still have it open? Please say it open. Yes. So the function is called map.
Yes, sorry.
2 arguments.
Yeah.
And then obviously consumption F# has the syntax let anything. Obviously let is a mutable thing, can't change it. You can define either a value or a function, so there is no difference between a value and a function. You could say let map error equals something, and it could either it could do an operation which returns a function itself and stores the sort of curried version of that function. So I'll just explain currying very simply. So we have let add equals x plus y. That's not right.
That's not right.
That is not right. I'm being an idiot, aren't I? And I don't need x.
No. Point 3.
There we go. Hands up. So the add function accepts an integer, and then you can add one argument to that function, which will return another function. So that's essentially what we're doing here. The add function is I accept 2 arguments and return a value, or you could see it as a single argument which returns a function which accepts a single argument which returns another value. and so on and so forth. And basically what we've done is we've added the number 2, we've added the x argument onto add, and now all we're doing is when we pass through, we'll pass through the y value when we call add 2. That's fundamentally how the F# type system works at its like lowest level in a terrible situation.
The functional equivalence of dependency injection, if you've used that before, it allows you to specify functions which, say you've got a function which gets a record from a database. If it's going to be pure, then it needs to be able to take the entire connection string or whatever. So you might actually define a function which takes the connection string, all the various other bits you need. However, you don't want to do that every time you call that function, so what you do is you just partially apply the function once with the connection string, and then you can just use that resulting function further on down.
To do your operations,
Yes.
etc.
Took me weeks to work that.
Oh, it's an absolute.
Amazing when a penny drop that.
You really start missing it.
Oh yeah, absolutely.
Well, I finally got it when I went back to C#. I was trying to do a load of stuff, and then it was like, I'm writing currying in C#. That's why.
I know. I'm going to say that don't try and write currying in C#. Just don't. It's just because you have to explicitly write the types everywhere. It just ruins it for you. It's just not worth the effort. I'll just leave it at that. So this is Chessy. There's a slight difference here in that Chessy has 3 states. It has a pass, a warn, and a fail. So you can have a successful value that is, and warn is actually built up of, and so it is the successful value and a list of the error values. So you can explicitly say, I want the OK value, or the warn value, or the fail value. So I don't particularly like it for that, because there's lots of functions that allow you to drop out and ignore the error, or discard it, or stuff like that. So I kind of favour using the original implementation. So actually, I'll go back to my. So this is the really cool part of F#, and that is computational expressions. So that pipeline we wrote in the last, in here, we have greater than, less than. You have to kind of learn what specific functions to call in order to actually, you have to learn the framework in order to actually use this value. What a computation expression does is it allows you to abstract over the fact that there is a library under the hood at all. So this is how F# does async. So you define computational expression block, and any function that we called a bind function before, so the construct function there, we've added the let, but we've also added the exclamation point there. And what that's done under the hood is that has implicitly applied the bind function here. So the value here is the unwrapped value of the result. If it was an error value, it will have escaped out and nothing, and you don't have to handle that error. You handle that error in the next half of the line. So just have a look at the type. And so before we'd have constructed that, we retain result int string, but initial value is just an int. So we've not had to call bind anywhere. That's done under the hood. So we've not had to unravel the value, or it's just available to us inside this computation expression. So we have the initial value. We can then feed that into our greater than value, a greater than function. So we partially apply that, or we apply int to that function, and that returns result int string. And then we've also got int as well. So obviously that is what we want. So at the very beginning I said we want to have something that's deferrable, simple, unambiguous, easy to consume, but the most important thing is that the simplicity is that it looks like code that you would have written anyway. And this is the advantage that computational expression gives you. Async was introduced in C# as a language feature that basically makes your non-async code look like synchronous code. you await at a specific point, and that is when you are doing the monadic transformation of, I am getting something from a remote resource, resolving it and returning it here. And the left-hand side, I've just got a value that I know how to deal with. And you know, it was built upon the work done inside of F#. The next thing down here. So we've done the same thing again, another apply function, left bang. And the interesting thing is we don't have to write a map function. Because lesser results is already the OK value from the previous phase above. We can just multiply it. And F# has a weird thing that it doesn't have the return function or the return keyword other than in computation expressions, weirdly enough. Because you can also do a result exclamation point, which will do a bind and then return under the hood. So that will reject it because it expects a result to be passed into that. So it will unravel that and then return. So there's loads of things that computational expressions do under the hood. And it's a bit of compiler magic. You add some special methods onto a specific type, and then all of a sudden, all this stuff, all these individual features get lit up. And you can use, like if statements. So you can say if greater than 10, or like the result of that, and that should unravel it and let you get access to it in the next block. So I think that's one really powerful part of F# specifically, and combining it with specifically result objects. There is also a async trial. So you have a type that just worked under that. Yeah, an async result. So you are doing some asynchronous operation, and you are also doing a result-based system in the same set of code. And that looks exactly the same, and we can just add in a function, that does some equals some asynchronous operation. Some async off. And then it does the same thing under the hood. So that is the kind of code that you want to write, but you can't because you have to think about errors. But it just handles that all under the hood for you. And I think that's one of the biggest arguments for F# as a language and this as a system. And I'll show you how you could write one of these yourself, because I have the code right here.
If you put that async result thing in there, it would break greater than 10 and less than 100, right?
Sorry.
If you had just put that async thing in there, you'd have broken greater than 10 and less than 100, right? Because the types are meant to do it.
Technically, it just implies that because you've got a result, that will wrap it. So it does all the stuff asynchronously, and then it wraps that in an async. So that's all still fine. That does the exact same thing, because that's compiling. I think I can run that as well. It's the consumption element. So my map failure function doesn't take an async result; it takes a result. So I have to write specifically probably map async failure error.
Yeah, and that computation expression would be fine.
Yes.
Yeah, that's pretty
Yeah,
cool.
the async builder, like the async result builder, will quite happily lift non-asynchronous values up to being async.
Cool.
So I'll get that code up now. So
Actually, that bit of code's kind of executing from bottom to top in a way, right?
what it does under the hood is something quite interesting. It looks at the functions and it basically unravels it into like a full expression.
Yeah.
So it will say like, so I'll just have a look at the code, or I'll just try and explain in terms of the specifics.
It's making me think of Scala.
Yes, yeah. So you would say when there is a left bang, it would wrap the. I've seen some examples online that would be very useful at this point in time. It's basically like it as you said, it kind of unravels the entire structure of your function into sort of like an explicitly sort of built, like, imagine when you're in C#, you have like a function that has like loads of other functions, and you've inlined everything into a single line, and you've got like add value, sort of like bind around it, and it just builds infinitely.
It kind of looks a little bit like callback hell in JavaScript, where it's just like lots of layers of nesting.
Yes,
nesting
yeah, that's what I'm trying to think.
and stuff.
I'm just trying to say the best way to describe it. But under the hood, the let exclamation point maps directly to bind, so you've got a bind function, and you say you have a type, and then under the hood, at the very bottom, I can't find the scroll.
If anyone saw my monoid talk the other month, that zero function at the top there is the identity
Is the
function.
identity function, yes. And all we're doing is we're saying we've built basically I'm trying to think now. We've built an object which contains all of our behaviour, and all we're doing is we're assigning it to this is my computation expression. I'm invoking that, I'm building that object, and this is the single-term computation expression that I have available to me. And that's the value that I use there. So it's not very much code for the kind of power that you get. So we have for, so we can iterate over it, so we can add for in loops inside of that block, which will unravel the result if there is a list of values inside, and then do something appropriately. We have try finally, so we can use try with blocks inside of there, and we have what do the other ones do? There's combine, which is addition, so you can plus. Is that's part of it? Is it the plus operator inside of computation expressions?
Yeah, I'm forgetting already.
I know. I know. And then there's obviously return and return from. So if I had return, that is that function there. If I had return exclamation point, it will just return, invoke this function. The zero function, as I said, is the identity function. So if you've got nothing already, it will just implicitly assume that. But this is a really powerful system, and if you learn it, you can do an absolute ton with it. So you can write like whole, people have written a computational expression builder for like HTML. So you have a different computational expressions like h1, div, p, etc. And you pass in a set of arguments for each one of those types, and it's like a very nice stylistic way of rendering views.
Can you then have custom operators? So instead of just allowing them to you have your own name things?
I'm not sure. That's in the computational expression. You can define your own operators that act upon your types within that computational expression. So you could define like a pipeline, your own version of a pipelining operator to use, because you're unraveling your values, you could just write those on top of the existing types.
Isn't that how query expressions are defined? It's a computation expression, but they have custom named things, so add
Yes,
or join
yes.
or whatever are custom named functions that they kind of have their own versions of.
And if it's there, it has the right shape of method, you can then use that. I have an example of that in C# specifically that I'll go into in a minute.
Sorry, is there a sort of interface or contracts that you have to define all of those?
No, you define any of them, and the features will light up as you add the appropriate one. So you don't have a return function. I think you have to have a certain number of them, don't you?
Return function and the bind function. I think the rest are all optional.
Yes. And then the language features will be turned on and off based on if they're appropriate for that context.
But yes, I think it all works on convention. I haven't had a look internally, but there doesn't seem to be anything magical you need to do.
You alluded to HTML, is that like Fable and that sort of thing?
Yeah, I think it's obviously Fable is it doesn't specifically have a view renderer inside. I think there's another library that will probably handle that computation expression.
Yeah. So Fable actually compiles the entire FShop program into an abstract syntax tree, which is what it then passes into Fable, which expects to get a JavaScript abstract syntax tree, and then spits out another JavaScript program compiled to whatever specification you're trying to do. So I think it works at a different level. It's kind of stupidly clever what Fable does.
We need to do what about these are all the computation expressions that you can do because they are so powerful.
Yeah.
Like you're saying, that's basically the big thing that came out of FShop X was just like.
I was watching FShop Conf last night, and yes, it was all computational expressions. All of this crazy stuff.
Because that's the power. You write the code the way you want it to look, but it handles all the modal transformations for you, and you don't have to have to think almost. You just have to know here I let exclamation point, here I return exclamation point. The same syntax that you use in your normal F# code, but like outside of the monad world, which is a really powerful concept. I thought I'd add that one in. So
Every time Charlie comes, he asks if we're going to do something on computational. So we're getting there slowly. So we've got some in.
might as well debug one before I get to the end of my F# section. I think I changed it before, didn't I? But I may not have stuck a breakpoint in, so it's just going to... Oh, no, there we go. So input, pass that straight to the computation expression. Inside there, and we can't step into the binds, so we can't see the bit that the framework under the hood is actually handling for us, because we're just microding, we're not bringing in the source of Chessie and saying, this is what I actually want you to step into. But I'm sure I could set that up if I had too much time. So we call the construct. Let's just stick that breakpoint back in and start again. There we go. So unraveled it to 11. We've not had to define our bind function anywhere. Pass that into the next stage. Great result. 11 again. Same again. Times by 2. And that came into our next phase on. So I think that is one of the things that F# specifically gives you over any other language. Computation questions is very powerful. So yeah, is there any questions about the F# stuff before I move on to plugging my own stuff? Cool. So I'll start off with a library called OneOf. So this is the C# language, the C# library that I've used quite heavily in the past, as of 2 people in the audience. So this is the syntax. So in C# you don't have type aliases. You can't say type result is equal to a discriminated union of these 3 cases. So you have to be very explicit about it. You have to say, I expect this function returns a user and a valid name or a name taken. So in this line, we basically use an implicit operator because the function arguments, the function return type is defined here. We will return new and valid name that will implicitly convert it to a OneOf for consumption later on. And then we'll move on. We'll do the actual operation. We'll get the item to the database. Then we'll check that item, and then if it fails the condition, we'll return another case in so these are the error cases. So this is, you can see kind of how result in C# would build into this. You would just have sort of result, user, and then an error case, could be list of strings, however you fancy. Do the action, return that thing. And if you have a look at the consumption, so we've got a discriminated union here. Obviously, you don't have to explicitly type that, it's not Java. We can put a var there. And the most powerful part of this library is the match function. The match function says, in order of left to right, I will pass in X number of functions that will return to me a type. So it's basically the consumption part of the F# part we talked about before. So when we have a user, I want to do this action. When we have an invalid name, I want to do this block of code. When I have a name taken, I want to do this block of code. And it will return a common type on the way back out.
How does that top function work?
Which one? The top one there?
Yeah. What's it doing to turn that into a OneOf?
I will show you. If you want to define this yourself, if you want to write your own version of this, that is a very big file as well. This is also generated code because of the ridiculous number of cases, but essentially it is this. So we have an implicit operator, so an implicit operator has to have either the input or the output being the type that you are contained within. So the type that we're looking at here is one of with 4 cases. So choice of in F# has up to 8 cases. So if we imagine it similarly to choice of, I'll zoom in on that because I can see you straight in on that.
Is it like an implicit cast or something?
Yes, it is an implicit cast.
Gotcha.
Yeah, I've only actually ever seen, before looking at one of, the only place I've really seen the implicit operator being used for is like builder app. So you've got the builder and then an implicit operator for turning it into the
immutable thing, yeah.
So this was
There we go.
interesting used here.
One caveat, implicits don't work against interfaces. So there is a function somewhere here, unless he's removed it. Yeah, from case. So you can say one of with your arguments, and you can say from this item, I want to build a result with this item. So if one of these arguments is an interface, that is how you construct it for consumption. Obviously, this is just a fundamental unit of like data algebra. You have plus types, which are we've all got objects with multiple properties on. That is essentially you are adding those pieces of data together to make a more appropriate piece of data for consumption somewhere else. One of is the bit that is missing from the negate. I have a choice of X number of items. How do I define that in C#? There's tons of ways of doing it, all of them wrong. You either have to define an abstract, sort of like you have to use inheritance, in which case you, as a consumer, aren't told what the possible cases are, because you can define an infinite number of them, and you always have a default case, and then always those exceptions, and we've all tried that, or we have a result type. It just goes on and on and on, and as the number of cases increases, the code becomes more complex to manage and maintain. And I think this is a good way of trying to manage that stuff. We're still living in the world of C#, so we still have to be very explicit about our result types, which is one of the common complaints about this library, is, wow, my return point looks massive. Just the type signature is huge. That's something we can't really avoid. But if we want to use it in C#, which is most people's day jobs here, I imagine, that could be a way in to teach people functional programming, because I know that's how I came into it, from C# and then building my functional knowledge and trying to replicate things from a functional programming background in the way that I do.
It's very honest, isn't it? It's the honest
Yeah,
API.
it's
like
the honest
there are
API.
3 return types, and there are 3 things that
There are 3 things that can go wrong with this function.
How does it combine with tasks?
Sorry,
How does it combine with tasks?
the same. You just have to wrap the thing in a task. You have to wait in the appropriate location. So obviously lambdas, you can have async lambdas. The one issue I always tend to find is if I have one in the match function, so I'll just go back to. So obviously C# doesn't do anything intelligent if you're doing a synchronous function and you want to return a task from that function. So for example, maybe this function here does something asynchronous, so I'll add async there, it will infer that that result type is now a task. But this isn't synchronous anymore, so either I have to attach async to that function, which then adds the sort of the task builder, splitting the function stuff that C# does when it has an async function, and it will complain at you a lot because you've not done anything awaiting there. So you can't have async without awaiting, it'll just complain at you. Or you do task.fromResult and decorate your result object, and that should infer up the chain. If you want to be more explicit about the result type that you're passing out, you can pass the generic argument into match to say, for these set of functions, I want to return this thing. That's typically what happens when the C# compiler struggles with the type inference. That's what you have to do, especially if you've got implicits of implicits, you know, like because view is implicitly convertible to, I think it's iAction result. There's nothing in there that says that, but if you had a task, it's just going to bomb out. C# really struggles with that kind of stuff. So you would have to say, brackets task iAction result here, and then that that kind of works with that. But obviously it's not as composable as F# is, as much as we would like to use so. So any questions about OneOf? It is just a fundamental, it is a building block that we build applications of, on top of. We've gone over to cognitive unions and the things that you can do with them. So I'll move on to the next bit. So I have written a railway-oriented programming library for C#. Because I think it's a really great paradigm. Obviously, we've just been talking about it for an hour and a half. So there are a couple of things that in C# we can't do compared to F#. Can't do functional composition. As I said, please don't. It's horrible. But what we can do is we can pipeline values. We can have a result type. So that's the same signature that we've seen in F#, and we can have a map function, a bind function, plus function, a fold function, a aggregation, a map errors, etc. So in terms of how you would represent this internally, we have 5 types in the library. So I've actually written an option type for C# inside of here. I've written a void result. A void result is an empty value and a list of strings as the errors. So we can have an empty result and a generic error. We can have a result that is just, we pass in T, and that is our result type, so it's no empty error, and a list of strings. So the idea is, the C, obviously we have to be very explicit about our result types. So if we had to add result, T error everywhere, that's going to create a lot of noise. And you kind of want to hide that away. So I've kind of tried to reduce the subset of generic arguments that you have to do in the appropriate places. And you can choose whether or not you return an enumerable string, which will convert into a different type of error later. But there's a lot of different things we can get from that. So like OneOf, there are implicit conversions between the 2 types of generic arguments to that result type. So there is an implicit converter from int into result into error, and there is an implicit converter from error into result int string of error. The one place I haven't done it is in result with just an enumerable strings. You have to use the extension method .ok because it will complain. If you use a result type of a string, which I imagine is very common, it will confuse the inference and it won't know whether it's an error or it's because there's implicit converters from a list of strings, an array of strings, and just string itself. So you could just return string, and that is an error. So you have to be explicit about this is if I have result of string, this is the OK value. This is implicitly converted to an error. So like with the F# result, we have a bind function that looks very, very similar to the function we had before. But we've also had to define the generic argument here. Interestingly, this is one of the things that really frustrated me when I was writing the library, because even though we have result int error here and we are returning here, we can't infer that that actually returns this. It just can't happen. C# has a massive overloading operator system that you can't infer the type of this function from that because it could be ambiguous because of default value overloads and stuff like that. It just doesn't work. So you have to define this is the thing that I'm returning here. So it's only applicable for this case and the result T case. So it looks very similar to OneOf in that we have a number greater than 0, we have match by action result, we have the same functions that are available to OneOf, and we can return an OK result, a bad request result from the consumption point. there. As I said, we have operation map bind t plus. So I've added, I'll show you some examples in a moment, but how we were talking about composition of values before. So how do you add together a result of t and t of error together? So what I've chosen to do for C# is a tuple. So we add two values together. We can add in an error adding function, or we can use I+. You can add I+ to your error object. That implicitly says to the plus function, I have something to add these errors together, so I will do so. The number of sort of operations grows exponentially in that case because you have 4 different versions of plus. You have plus with neither of the generic arguments having I+. You have it with one of them, and you have them with both. So that's 4 cases. But I think it really simplifies your code because your error handling object has the behavior built in to add them together. I couldn't think of a better way to do that in C#. I'll try and show you an example of that. Or if you don't actually have an addition type for t, because you might have t1, t2, it will convert them into a value tuple. So you'll have, if you have result t1, result t2, you plus them together, you will end up with result tuple t1, t2. So add them together. So I think that is quite a nice way of doing it. And I have added everything, as you said before. How does this play with async? I've added tons of async overloads and operators. So either the operand is a task, so it could be task result t. What are the operations we can do on that? We could do a map bind t, every function that is available in the non-async world. And we can also have the function that is being passed into it returning as a task as well. So there are an extra 3 overloads for tasks. So I've just kind of gone over the README. I obviously don't have anything prepared for this, but I'll get to the code and just sort of see a set of examples. So I'll just show you the code and show you how you could write something like this in C#. I didn't actually show. Following on from computation expressions, I have test, which shows us how we can add, how we can write. So what this does is, you know, you were saying as well before about when you build query expressions in C#, you can write them against any generic type. IEnumerable is one of the versions. So we have a value here, okay, from s in, so that will unwrap it if it's successful, and give us the value s. And then we're going to do some operation on it, that is our map function, and then we're going to return a result type to operate upon. We have also, we can do map on 2 values, so we have the value from before, we have our next error, we do that together. So if both of those values are successful, we'll give you a scope for them, and then we'll return a new result wrapping that value. So that's one little part of the library. So under the hood, I store it as a one-off because why not? We've got a common discriminated union pattern under the hood that we can use. Implicit internal constructors, so you can't call them unless you use reflection. We have the implicit converters from an error type or a T type, because otherwise you would have to say, use the extension method fail with all the generic arguments. So you have to say what I'm actually operating upon and what type of error I am actually using in this scope as well, which really would just defeat the purpose of the whole library. We have match function here. So that has basically the same signature as error in. Oh, there we go. The same signature as F#. You have not F#, OneOf. You have one result type, one generic argument, X number of functions based on the number of things that you have, and you will invoke those functions. So pretty much every operation in this library is a single line, like in F#. So you can build up more and more complex operations based on your use cases and usages of. And there's the bind function. So we do a match on, and if it's an OK value, we pass the bind function to it directly. Otherwise, we just fail. We just pass the error that was given to us and pass it back out as a failure. Map is essentially, I want to map both of them. The ID function in F#, we didn't show that before, but the ID function is available globally in F#, and that is essentially the same as X returns X. It's just a function for taking a value you have and returning it as a shorthand. You don't want to define a lambda every time you just take a value and then pass it back through again. I've defined it here inside of my library. Don't have that many great examples. So this is what I was saying about addition. So if you want to add together, obviously you writing this code yourself would be crazy in C#. So the idea is that I've just hidden everything under the hood for you and given you as many overloads as you might ever imagine, and I'll add many more in to sort of hide away the fact that so if we want to add two items together, we don't know how to add the error together, but we haven't added an operation to add T1, T0 and T1 together. So we actually just return, there's three operands on this one, but it'll just return the tuple of X number of arguments. So you can add together as many results as you want, up to 8, because that's the limit on a tuple. And then once you've added together all of your results, you can then map on that and convert it to your final object to pass up a level again. So you can see how this kind of builds on a lot of the concepts that are available in F#, or tries to emulate them in a C# idiomatic way. So that's the difference. Everything I've tried to do here, I've tried to make it as C# friendly as possible.
I've never seen people have put that on fault before.
I wrote that. Wrote a set of extension functions that say if I have a tuple that has the left-hand side being a tuple itself of two arguments, I will call operation called unfold, which flattens it and then converts it into a larger tuple, which I think is quite a useful thing in and of itself. I've played around with the idea of using this pattern to add together tasks. So you have two tasks and you've sort of remotely resolve them from a web server, and you want to add them together. You don't want to await both of them individually. You can just plus them together and you'll get a task of a value tuple, which I think fits in quite well, and you could do sort of coordination of multiple operations and then pull them together, and then maybe have a map function in there as well, just for the sake of it, because awaiting is something that you don't want to do all the time. You just want to return the value straight back out. You don't want to actually await it. That's the difference. So you don't actually await anywhere, because awaits have a cost, because it actually splits the method in half and does a load of compile magic under the hood to restart your method at that point. You could just write a map function and not have to deal with the overhead of that.
Sorry, why have you stuck the decomposition? That's decomposition going on there, right? Where you can
Yes.
start to why have you stuck that with two lines?
Which one? That one there?
Well, all the examples, you got tuples is you're increasing the number of parameters. You split it over 2 lines, you've got like 2 lines and 4 equals I.
That is a very good point. I haven't actually tried that and see if it works like that. You alright? Thank you. So yeah, it's just a utility to actually unravel it. I think there are actually, they are thinking about doing something quite soon whereby you can implicitly deconstruct tuples in lambdas. So you write like an extra pair of parentheses around, and that will automatically deconstruct it inside the argument, which will make usages of like value tasks much more useful rather than directly accessing it. It's basically destructed in the function you pass into it, which I think would be quite useful. I can go into this a bit more, but I haven't really prepared anything or like a set of demos to explain this library. I wanted to come at it from a purely F# perspective, explain all the concepts, and hopefully all the concepts make sense in this library, in this world. And it'd be a good thing to just have play with and see what's like.
This would be a good time to
Yeah.
move to questions because we're running short on
We're
time.
short on time, yeah. Fair enough.
It's really cool stuff that you see that.
It's absolutely nuts to get my head around. It's really, really nuts. But I've used it, I think, quite well at my current work, and it's very useful for sort of those basically web services. You have status pipelines, and it's very useful for all the reasons we talked about in F# and carry over into this library. For it depends. You may struggle more as your solution gets more complex compared to the F# implementation. That's what I would say would be the pitfall of this. But we all can't make an F#, unfortunately. So
That's the problem, isn't it?
that is exactly the problem.
I mean,
That's why.
I mean, this is lovely, but I mean,
Exactly.
Use F#.
Use F#, exactly. Why are we shoehorning features into a language that doesn't support it? That is obviously a valid thing to do. But I think I've managed to abstract away a lot of the pain of dealing with the results, the railway-oriented programming within C#. So, yeah, that's... Any other questions?
Do you think your C# would be quite good as an argument of why you should use F#? Because to a lot of people, because I know C#, but that looks very complicated
Yes.
to me, and the F# almost looks easier,
Yes,
even though I don't
exactly.
know the language.
Yes.
So even if you know F# at your work, you'd say, well, who else can maintain that if I'm ill? And you'd be like, no, just use F#, and then the language does it for
The
you.
language is for you. I mean, the point of this library is to abstract away all that pain. So the consumption API we saw was a lot better compared. It was almost the same as the F# consumption that we've seen before without the functional composition. So you can just write pure pipelines, pass around results as we would, and there's structs as well. So copying of references, etc. All that stuff applies. Comparisons doesn't. I've never thought about structural quality in terms of this. And obviously, structural quality is a massive problem in C# anyway. Let's not get into that. Yeah, I thought it was an interesting experiment, and I've obviously, as I said, I've used it in a project, and I think it works really well. So it may be something you could just hack around with, see if it will work for you guys. Yeah. Cool. Thanks everyone for coming.